Hello and welcome! In the last video we talked a lot about the fundamental theorem of calculus and how these ideas of the integral and the derivative are inverses of each other. Well, from this idea comes the indefinite integral. So really, back in chapter 4.9, we were talking about the antiderivative. This function who undoes the derivative. And now, the really cool thing about that is we can now take a look at we now have a notation that looks like something we know, or symbolizes at least the antiderivative. And that notation is this integral, the integral of f of x dx. And that is quite literally just equal to capital F of x. So, really, the integral of f of x dx means that f prime is equal to f of x. So now what I just want us to do is really just evaluate these integrals. It's probably not going to be that long of a video. So let me ask you this way. What is the antiderivative of 3x squared? Well, what do you have to take the derivative of to get 3x squared? X cubed. So we get x cubed. What is the antiderivative of 4x? It's going to be 2x squared, as it's going to be raised the power by 1 and divide by 2, plus x. And now, because we are evaluating this a lot like a normal integral, however, because this does not have bounds, hence the name indefinite, rather than adding a or subtracting or evaluating, what we have to do is we just have to add a constant c to symbolize the constant that gets rid of whenever we take the derivative of this. So as you can see, we'll get 3x squared plus 4x plus 1. But the c always goes away, so that's why we have the c there. Well, now let's ask, what is the antiderivative of e to the x? Well, the derivative of e to the x is e to the x, and we're about to learn that the integral of e to the x is also e to the x. It's so cool. Such a great function. Well, now, what is the antiderivative of 1 over x? Well, let's think for a moment. That's that we can't raise the power by 1, because that'll give us 0 over 0. But what we can do is we know that the derivative of the natural log of x is the 1 over x. So we know that this is just 1 over x. The natural log of x, sorry. However, we also have to include the absolute value, because 1 over x is defined for all real numbers, but the natural log isn't, but the absolute value makes it so it is. Alrighty. Well, now what we're going to do is we're going to look at the integral of sine of x plus cosine of x. And you might notice that I'm now swapping to saying the integral, and that's normally what most mathematicians will say. Well, the integral of sine is going to be negative cosine. We have to really think backwards here. What function's derivative is going to give us sine? And that's going to be negative cosine of x. What function gives us the integral of sine? It's going to be the derivative of sine. And then we have to remember always our plus c. Alrighty, for these next few integrals, the integral of 2, and it looks like I forgot dx, is going to be 2x. Well, what is the integral of an exponential that is not 3 to the x, or not e to the x? Well, let's take the derivative of it and look at that. Well, we get the natural log of 3 times by 3 to the power of x. Well, because the integral and the derivative are these inverse functions, I think it's easy to reason that the integral of an exponential is going to take the form of the natural log of the exponential divided by b to the power, or b to the power of x divided by the natural log of b. Just because these functions are inverses, like multiplication and division are inverses. So we get b to the x divided by the natural log of, 3 to the x divided by the natural log of 3. And always remember your constant of integration. Alrighty, now for this next problem. This one, for the most part, we're going to have to work out using our inverse power rule. So we get x cubed. We increase the power by 1, and we're going to multiply by the reciprocal of the power. So this is really x to the power of 0. So we're just going to raise the power of the x to 1, and then divide by 1. So we just get x. Well, we can't raise an x to the power here. But let's think for a moment. What function has an integral, or rather a derivative, that is 1 over x squared? And as you're thinking about that, let's think that that is going to be, well, it's one of those inverse trigs. It's going to be the inverse tangent of x. And then we just have to add our constant of integration. For this next integral, the integral is not, how do I say this, distributable. We can't say that this is going to be the integral of sine of 2x divided by the integral of sine of x. We can't do that. So we're going to have to find a way to simplify this expression, and we can do that using some of our trig identities. Thinking back to maybe whenever we took Math 1405 or some other math class, or a trig class, or whenever we were in pre-calc, the derivative, or sorry, not the derivative, but sine of 2x is the same thing as 2 times by sine of x plus, or times by cosine of x. And that is still over sine of x. Well, now what we can do is we can cancel the two signs, so we're left with the integral of 2 times by cosine of x. We can use our properties of the antiderivative here to call this 2. And I suppose I should talk a bit more about the properties of the indefinite integral, but I'll do that another day. We can take out this 2 on the outside of the bounds, just like we can do with the derivative, and call this the integral of cosine of x dx. Well, the integral of cosine is just sine, so we get the 2 sine of x dx. Or sorry, 2 sine of x dx. There we go, yeah. For this next one, we don't have a way of integrating a product just yet, so let's multiply this out. So we get the integral of secant squared of x plus secant of x times by tangent of x. Well, let's think for a moment. What function, when we take the derivative of, gives us secant? It's going to be tangent of x. Well, what function gives us secant tangent when we take the derivative of it? It's going to be secant of x. And always remember the plus c, which looks like I forgot last time. And I don't know why I wrote a dx up there. That was totally my constant. So, now I just want to change my focus to, like, really just highlighting something from yesterday's video. And this is the net change theorem. The integral of a rate of change is the net change. So really that's saying is, if we have a rate of change, let's say f prime of x, and we're integrating from a to b, the net change of that function, f of x, is going to be f of b minus f of a. So these are often going to come up in word problems. So we're going to say if w prime of t is the growth rate of a child in pounds per year, what does the integral from 5 to 10 of w prime of t represent? And what we would say is the integral from 5 to 10 of w of t dt represents the net change, or the net, I suppose that it would be like pounds. The net change in pounds from 5 to 10 years. There's a small bit of information missing, like, is this months or is this years? But I'm going to say it's going to be years. I don't know if it's from 0, though, so I'm going to say it's probably a good way of saying this is the integral from 5 to 10 of w prime of t dt represents the net change in weight of a child from year 5 to 10. So you have to be very specific, like its weight, and sometimes you might even want to be a bit more specific and say weight in pounds. Really, you just want to be as specific as possible, depending on who's teaching you the class, but I think weight just deals with it for us. Alrighty, and then for this next one, I think this one's a small bit more challenging, but if h of t is the person's heart rate in beats per minute t minutes into our exercise, what does the integral from 0 to 30 of h of t dt represent? So really what this represents is going to be the net change in beats per, or sorry, the net change in beats from 0 to 30, or from from 0 minutes to 30 minutes into the workout. So we'd write this as the integral from 0 to 30 of h of t dt represents, and sorry, this is kind of becoming an English class, but that's why I'm doing this at the end, represents the net change of beats from the start of the workout, to 30 minutes in. 30 minutes in. The workout. Alright. And of course, if you ever want to be more specific, that's always welcome. I'm pretty sure no one will ever dock you for ever being more specific. But I hope this video has kind of helped you get the basic understanding of the indefinite integral. And if you've watched to the end, I want to say thank you for watching. Hope you all have a wonderful rest of your evening. And enjoyed. Goodbye.